So I'm going to show you some magic trick right now. You all know factorial functions and how to calculate factorials, but calculating factorial is actually quite heavy on the CPU and also it is slow. But what we can actually do is we can make a compile time factorial so that all the calculation that is done at the compile time, and at the runtime we just print the result. So obviously let's start with int main, and this is obviously done using template programming if you would have guessed. So let's go with template int t, or just go with a big int 128 t, and let's have a struct called factorial. Okay, then factorial will have a static const expression, const exp value, that's the factorial, and it will be t times factorial of t minus 1 value. Okay, so it needs a type specifier. Let's go with int 128, or actually instead of int 128 let's go with u int 128t, u int 128t. That's now we need some base case, so we are going to say inherit the template declaration of struct factorial. If the input is 1, the value would be, just yank this thing and just go end and set the value to be 1. Same will be for 0, so just yank 3 lines and paste. Just go with 0 and that's it. Now we can go factorial of suppose let's go with factorial of 10 value, and we can start out this thing, and obviously we now need to overload the the cout thing for u int 128. So what actually happened, u int 128t isn't supported by stud out, so you have to overload the operator. So let's quickly just overload the operator. Okay, so we have had this thing actually quite nice. Now we need to fragment our u int 128t into parts, and then we will be start couting those parts. So just quickly have a while value, I guess, or let's have u int 128t value, val is value, and while obviously I can start out this thing. So I have to take modulo and start out the modulo, so it will start out in reverse. So I want it to start out not in reverse. Okay, let's have a quick stud string output. Just go with output. So output should be empty. Output plus equals val mod 10, and output val divide equals 10, and plus character 0. So this is nice. We have to return an output stream, so return out output. So this should print it in reverse. So yes, it printed that thing in reverse. Before putting it in, just go with the std reverse output dot begin comma output dot end, and now it should print correctly. Okay, so this is obvious correct, and we can now calculate factorial of any number up to, I guess, 31, cause after that it will overflow the int 128, and it is literally 0 seconds in user and system time. The compilation part did everything, and you could actually test this against a normal factorial calculator. So we can go something like uint 128t fact, so function that takes in uint 128tv and returns v times factorial of v minus 1. Okay, so this is the exact same logic that we used for the template thing, and if I just check this to be something like factorial, no, not this, man, just go fact of 31. I just want you to see the time that it takes, so let's just compile this and time. Okay, it got set fault because we didn't have any base case. Okay, if v equals 0 or v equals 1, return 1. Okay, now it should work. It still took less time in, okay, so in nanoseconds it should work. So let's go start the chrono, high resolution clock now, and let's go auto start to be this thing, and let's go auto end to be this thing, and see out the factorial, and obviously end this thing, and start see out time in nanosecond. So let's go with static cast to start chrono nanosecond, and static cast end minus start dot count. That's it. So it should now give me the time. So let's go. It took 280 nanoseconds to calculate the factorial, and if I replace this with the value that's factorial of 31 value, it actually took more. No, I forgot to compile. It took 110 nanoseconds, so almost 3 times less the total time that it took to calculate this number. Also, for small factorial like 31 factorial, this thing isn't that significant. But when you calculate factorials of digits that are greater than suppose 100, then obviously the first bottleneck will be the data type that you are using, but the second bottleneck will be the algorithm that you're using. And if you're using a naive algorithm like this thing, it will be tremendously slow. So again, template meta programming made life easier, and we are now able to calculate factorials that are compile time calculated instead of runtime calculated. So it's like you will be getting a direct value when you use factorial, but if you use the function, you will be calling a function and you will be having its return value, the runtime value placed in fact. So yeah, that's it for today, I guess, and bye.